Hello, you're welcome back. All right, so we gonna continue from where we stopped. So now we're gonna look at equipotential surface. Okay, so as the name implies, an equipotential surface is a surface of equal potential. Okay, we already know, okay, previously that the electric potential at any point in an electric field is given by the formula KQ. Okay, all over R. So Q is the charge. So which simply means that the R, okay, the distance, or in this case now I have a sphere, the R is the radius. So when the distance from that charge is the same, at any point on that particular surface, the potential will be equal, all right? For example, I have a charge at the center of concentric circles, okay, three circles, all right? So now let's start with the very first circle. You discover that the distance at any point, okay, of that particular four circles, at any surface of this four circle from the charge is the same distance. That way I can simply say that the first circle, okay, any point in this first circle will give what is known as equipotential surface, okay, because the surface will actually yield equal potential at any point. The same happen with the second sphere or circle. At any point in the second circle from this charge, you have an equal potential, and the same with the third. Okay, so an equipotential surface is a surface with equal potential. Now, because a surface has an equal potential, don't forget that uh, from our definition of electric potential, we said electric potential is the work done in moving a unit charge, work per unit charge. So if I should cross multiply, that simply means that the work that is done in moving a unit charge is going to be equal to the potential, electric potential, then multiplied by the charge. So now, if we have an equipotential surface, it's called that the potential difference between the two points in that surface, all right? The potential difference, let me use delta V, between 2 points on that surface is equal to zero. And if the potential difference is equal to zero because it's equal, all right, then that simply means that in an equipotential surface, no work is done, all right? So work done on an equipotential surface is always equal to zero, okay? So please take note. So the characteristics of an equipotential surface is that it's a surface of an equal potential, and there is no work done in moving a charge, okay, around an equipotential surface. The work done in moving a charge is actually equal to zero. So please take note of that. All right, as we actually proceed. Okay. Now we are going to look at something. Okay, here we'll look at the relationship between, okay, relationship between electric potential and electric field intensity. We have actually treated these two parameters. Okay, relationship between electric potential, electric field intensity, and electric potential V. So relationship between E and V. Now, how do we actually establish this mathematical relationship? It will be very easy. Okay, we already know from our definition that electric potential is equal to the work done in moving a unit charge. And we also know that, okay, work is equal to force times distance. Let me use D this time around, divided by charge. Okay? But I hope you can still remember the formula for electric field intensity. Remember, okay, we said that electric field intensity is given as force per unit charge. So now from this formula now, so we can conclude that, okay, electric potential is going to be equal to force per unit charge, which of course is electric field, then multiplied by the distance. So the relationship between electric potential and the electric field is equal to electric potential is equal to electric field multiplied by distance. That is why, okay, I can actually express electric field again, apart from the formula we've known before, to be equal to the electric potential then divided by distance. All right. So by SI units, electric potential can also be given as volts then per meter. Okay, apart from the Newton per coulombs that we know, electric potential can also be expressed as volt per meter. Why? Because it's given as voltage then divided by the distance. So these are very important relationship that you should write somewhere, because question in examination will require you using either of this formula to solve it. All right. So we're going to be looking at more examination question. I will be picking some questions, then we will do justice to them. Okay. So here we are. Okay. I'm going to start with this particular question. It's a question on electric potential. Then we're going to work on it. Okay. So I bring it to right to the screen. Here we go. All right. So this goes this way. Find the electric potential at point A and B. Okay, so I have 2 points. I want to find the electric potential. This is point A. Here is the point A, and here is the point B. All right. So now let's proceed. Due to two sphere X and Y, so there are two sphere X and of course another sphere here Y. 1 meter apart, of course, is indicated in diagram. In air carrying charges of 2.0 times 10 to the power minus 8. That means this sphere here at x, the charge is 2.0 times 10 to the power minus 8, and that is a positive charge plus. And of course, the sphere at y, the charge is minus 2.0, then times 10 raised to the power of 9. Okay, so we are being asked to find the electric potential at point A and point B due to these charges, and I believe that will be very simple. Okay, so let me start with electric potential at point A, VA. Of course, so electric potential at point A is going to be due to the two charges, and you know how we actually sum electric potential at a point due to two charges. Okay, so that's going to be equal to by formula. Okay, I can simply, you know how we do that, you know the formula already. That's gonna be K bracket open the charge at X. Let me use QX to represent that. Then divided by the distance of X from A. I can use RX to represent that. Then plus the charge at Y. That is gonna be QY. Then divided by the distance of Y from A. Let me call that RY. So the potential at point A, let's flow. Okay, let's flow. So putting our value, we have K to be equal to 9 times 10 raised to the power of 9. You already know that. Then open bracket, charge at S is 2 times 10 raised to the power of minus 8. Then divided by the Rx distance, that's 1 meter. Okay, so I put that 1 meter. Then this is gonna be plus. Okay, the charge at the charge at y. Okay, the charge at y already is negative. It's a negative charge, so it will affect this plus here. That's gonna give me minus. Okay, so I'm gonna have minus 2.0, then times 10 raised to the power of 9. Okay, then the distance. Now the distance all the way from Y to A, that should be 2 meter. 1 plus 1, and that's 2 meter. Okay, so let's finalize our answer. So this is gonna be equal to 9 times 10 raised to the power of 9 bracket open. Okay, so when you divide this by 1, I will have 2 times 10 raised to the power of minus 8. When I divide this by 2, 2 cancels 2, I'm left with, oh, please pardon me. This is still 10 raised to the power minus 8. Okay, please pardon me. The charge at, okay, so the charge here is raised to the power of minus 8. Is the same quantity of charge with this, but negative. So please pardon me. Pardon my mistake. So still minus 8 raised to the power of minus 8. Okay, so here 2 divide 2, I'm gonna have 1. Okay, so 1 times 10 raised to the power of minus 8. Okay, so here we go. So of course, in this case now I can factorize since 10 raised to the power minus 8 is actually a common factor. I'll take it out. So I'm going to have 9 times 10 raised to the power of 9, then times 10 raised to the power of minus 8. 10 raised to the power minus 8 is a common factor in the brackets, okay? It's a common factor, so I take it out. Then I open the brackets, I'm now left with 2 minus 1. Okay, so VA now is going to be equal to, all right, 2 minus 1 is 1, all right? And of course, 1 times 9 is 9. Then 10 raised to the power 9 times 10 raised to the power minus 8. That's going to give me 10 raised to the power 1, which is same as 10, right? So that is gonna be 90 volts. That's 90 volts. Okay, so I hope that is well understood. So now, what then now happens to point B? Point B is the same thing. I'm gonna do this. Gonna be the same solution, but the difference, okay, for the potential at point B is that the distance of Y from B is 1 meter, unlike the distance of Y from A, which was 2 meters. So I believe that you can be able to evaluate that. Okay, the potential at point B is gonna be the potential due to X, and of course, uh, plus the potential due to Y. So I believe you can do that. Okay, so I hope that is well understood. All right, let's proceed. I can also get more questions. I have more questions here that I want us to actually do justice to. Okay, so this question now is still based on potential, electric potential. So it goes this way: find the potential at 2 point A and B at the distance 1 cm, 10 cm, and 50 cm from a charge of 2 microcoulombs as shown in figure 3.8. This is the figure here. So we are looking at the potential. We want to find the potential at both point A and point B. You know how we do that. The potential at point A is going to be due to the charge 2 microcoulombs, and of course the charge 0.05 microcoulombs, okay, from this point. So that will be easy. Let's actually do that. So the potential at point A, Ka, is going to be equal to, of course, K, okay. So I can just probably put the value at once, K, which of course is 9 times 10 raised to the power of 9, bracket open, the charge of 2 microcoulombs, then divided by the distance of that charge from point A, that's 10 cm, which is 0.1. Okay, then plus the charge at B. Let's evaluate that. 0.05 times 10 raised to the power of minus 6, then divided by the distance from all the way from B to A. Okay, so we already told that from A to B, the distance apart is actually 50 cm. So invariably now, so I hope you understand how I'll be able to that the distance between A Okay, or please pardon me. Okay, we are told that distance from between A and B is 50 cm apart. Okay, all right. So now let me put that value there. So 50 cm actually convert it to meter. I'm gonna have 0.5. All right. So let's get our work. Let's finish up. So what do we have here? This is gonna be 2 divided by 0.1, that's 20. So I'm having 20 and 0.5, 0.05 divided by zero point 0.5. What do we have? 0.05 divided by zero point 0.5. That's 0.1. Okay. So in this case now I'm having 9 times 10 raised to the power of 9. Open bracket. I have 20. Okay, then times 10 raised to the power of minus 6 plus 0.1 times 10 raised to the power of minus 6, bracket closed. So of course you know very well what I'm gonna do. Common factor in the bracket is 10 raised to the power minus 6. I take it out. So I'm gonna have 9 times 10 raised to the power of minus 6. 10 raised to the power 9 times 10 raised to the power minus 6. Okay, so now we have okay, please pardon me. Now we have 10 raised to the power of minus 6. Okay, 20 minus 0.1 is approximately 20. So it's still approximately 20. So I don't need to do that. So I'm having 9 times 20. That's gonna be 9 times 20. Okay, so that's 180. 180 times 10 to the power 3, which of course is kilovolt. Okay, so that is the the potential, electric potential. Please pardon me. That should be VA, electric potential at point A, not KA. Please pardon me. The symbol is VA. Okay, so the next is we're gonna get the electric potential at point B. Now the electric potential at point B, okay, we only be the potential at point B due to the charge of 2 microcoulombs. The charge at 0.05 microcoulomb will not create any potential. Why? Because it is already at point B. There's no work done in moving a charge at the same position, okay, to that same position. So the work of 0.05 coulomb is 0. So the only work that you get is the work due to the charge of 2 microcoulombs. So in that case, now I'm looking at just 9 times 10 raised to the power of 9 multiplied by the charge 2 times 10 raised to the power of minus 6. Okay, then divided by the distance of the charge of 2 microcoulombs all the way to B. Of course, you know that what that will be 10 plus 10, 10 plus 50. Okay, that's 60 cm, which is zero point 0.6 eventually, because the distance from 2 microcoulombs to A is 10 cm and the distance from A to B is 50 cm. So when you combine it together, 10 plus 50, that gives me 60. So if you divide that, you're gonna have 0.6. So let's actually okay get over with that. So I'm gonna have 9 times 2 then divided by 0.6. So I'm gonna have 30. Okay, so of course 30 times 10 raised to the power of 3, which of course is same as 30 kilovolt. So that is it. As simple as that. As simple as that. Okay, let's proceed with more question. Let's proceed with more question. If I can see one, can I see one here? Okay, so I can get more question probably in the next video, right? Okay, see you in the next video. Thank you very much.